Load paths. So what are load paths and why are they important? A load path is the way that a load travels from where the load is applied to its final destination, which is usually the ground. They enable us to understand how the structure will work and behave so that we can make accurate estimates on how they're going to act when we carry out some structural amendments. Incorrect assumptions on load paths can cause structural instability, cracking, failures, unexpected loadings, which can lead to catastrophic effects. And it's very important that they are understood so that we can avoid unsafe conditions on site. So we're going to have a quick couple of examples here. On this simple structure here, I've just stopped him before he does the deed that he's going to do, but on this simple structure here, we can see that the load from the roof is able to travel across the wall plate or the header beam and then down the walls on either side. And this is important because it's about to crash through it. So clearly we don't kind of condone that kind of behavior, and it demonstrates, what it does do is it demonstrates that having a viable load path that can sustain the applied loadings means that the whole roof didn't come crashing down on top of him when he did some kind of stunt like off of a James Bond film. The next example shows how the load path in this reinforced concrete box structure has slowly changed during demolition, and the load that is coming from the self-weight of the structure is being transferred to the rear, but eventually this load and the stresses from the resulting moments, they become too great and then we get a failure. I don't think this was the desired outcome, but nevertheless, again, it demonstrates an example on how load paths can change. BS 6187 is the code of practice for full and partial demolition. Load paths in structures that are being demolished change regularly. Therefore, it's a residual risk on complex structures. Unplanned collapses can occur and should be avoided if we fully understand how a structure works and therefore how it will behave when we start removing certain structural elements. The word load path comes up a number of times in this document, and that's understandable as the construction information on a structure being demolished is not always available, as opposed to a new structure being built where we have all the details to hand. Therefore, the chances of misunderstanding is greater for a structure during demolition. A key section where load paths are mentioned is in section 14, where it states that any demolition should be based on a complete understanding of the nature of the structure, the interdependence of all the structural elements, and the interrelationships with adjacent structures and the surrounding environment. It goes on to say that the understanding the load paths is essential to enable the strategic use of the inherent structural interrelationships, which, put simply, is relying on the structure standing up during the demolition works. The same applies to new structures being constructed, as this is essentially the reverse of demolition, or demolition is the reverse of construction, but whichever way you look at it, the stability of the structure relies on a good understanding of how the structure works, of which load paths is a very large part. So what happens if we get it wrong? What happens if we think a structure behaves in one way and it actually behaves differently? Well, potentially catastrophic effects. And it comes down to GIGO, which is garbage in and garbage out, something that we drill into a lot into us at Andon, and it's very important because without a full and detailed understanding of how a structure behaves, we can't get the right output. We need to feed ourselves with the correct information, which may be structural drawings or site investigation, and that gives us a proper understanding that we require to determine the correct solution. So now we know that a load path is the way that a load travels from where the load is applied to its final destination. We'll now briefly discuss on what those loads could be. So these can be broadly split up into two categories. That is vertical loading and horizontal loadings or lateral loadings. The vertical loads, these could be gravity loadings, such as the self-weight of the building acting down due to gravity. Imposed loadings, these could be live loadings, such as pedestrian loadings, vehicles, environmental loading such as snow. And then we have lateral loadings. These could be gravity, such as the self-weight of soil acting onto the structure, or if the structure is leaning over, you'll get a lateral loading from that gravitational pull effect. And the lateral loadings from imposed loadings could be wind or waves and things like that. It's also important to consider that you may get combined load cases where these forces can all act together and follow the same load path. Here we have a very conventional load path on a basic structure. This could be a reinforced concrete slab on concrete or steel frame, comprising of beams and columns that are themselves founded on pad foundations. As the illustration shows, the load on the slab follows the structure from the slab to the beam, to the columns, and then finally to the foundation, where an equal and opposite reaction resists that, in the ground, resists that total loading. Here we have another basic structure with a more domestic type arrangement. And again, we have the loading from the roof and the other structures coming down and ultimately being resisted by the foundations. Here is a real life example of the slab and steel frame kind of structure. So the load moves from the slab to the secondary beams, and then from the secondaries to the primary beams, and then from those primary beams down to columns, and then the load will go down from the columns to the foundations. Here we have a propping scheme, and again we're seeing a very similar pattern. We've got the load coming from the slab to this slab edge, and then across to the structure, whether it be a beam or a proprietary beam that we've put in, and then down from there to the columns, and then to the foundations, where we get a reaction resisting those loadings. These are conventional and quite basic load paths. Here's an example of the structure that threw up an interesting detail that we weren't expecting. So what we have here is an external wall of a large portal frame shed. The wind post ran vertically down the building all the way down to foundation level. We needed to remove a column to allow some large plant to access into the structure and carry out some demolition works. So that meant either removing the red column or the green column. Either one would do, and it would give us enough space to get through there. But upon exposing the structure, we saw this detail here. So what we had is a pin support directly adjacent to a column. Therefore, if we removed that green column on the left, just next to this pin support, then the structure above would not have been supported properly. However, removing the red column, that could be removed as there was a suitable structure to transfer the load safely back down through the remaining structure. So therefore, by understanding what was going on here, we were able to safely do what we needed to do to allow works to progress. So now we'll have a look at an example of a load transfer structure. In the bottom of this basement, we have a steel frame that we designed to support a reinforced concrete party wall while new foundations were constructed. The frame was founded on some plunge piles, so some plunge columns in the piles, and then picked up the load of the party wall, jacking it up slightly, and then transferring that load from the wall back down into the piles. We've got some photos here that I took during the jacking works, and the load from the party wall is transferred into the frame and then down into the piles, a little bit like this. So we've got the load from the wall, and that's offset from this frame. Therefore, the back leg is in tension, it's being pulled out, and the front leg is in compression, being pushed down. It's very important that this frame was really stiff, as we could not afford any damage in the party wall. An in-depth understanding of the load paths involved here was key to maintain the stability of the structure and also minimizing the damage to third-party structures. So there's some examples of load paths transfer and how conventional load paths work. But how do we know what the load path is? Well, we need to have that in-depth understanding of the structure, which is developed from a desktop study and intrusive site investigation. And it's important that a competent person reviews this information is also confident in their conclusions. Sometimes the simplest operations, such as creating a door opening, as shown in this example on the right-hand side there, that can include some very tricky load paths which must be considered, especially when you're altering a structure which has already been altered before. There's some complex load path arrangements that need to be properly considered. So what does that mean in real life projects? Well, having a thorough understanding of structures and how they work, typical structural arrangements, experience with similar structures, that helps a great deal. It means reviewing archive drawings, that's if they're available, that is. Remembering that just because they're archive drawings, it does not mean that they are as-built drawings. Intrusive site investigations such as breakouts in the structure to expose the key structural elements, confirming assumptions or finding out new information if you don't have drawings of the structure. And it's also a good idea to have a good walk around and as a walkover survey post soft strip so that you can have a good look at the bare structure and the structural elements that you have there. This is going to give you a good understanding of how the structure works and what the load paths are. So here we've got a few items that need to be considered when it comes to load paths. How is the structure currently standing up? Chase the load from all the way to the top to the bottom where the foundations are and justify to yourself how this structure is able to remain standing. How does the load path change if there's any settlement? If a support drops, then where does the load go? Is there any redundancy? Is that an issue? Sometimes this isn't when a structure is being demolished anyway, but that needs considering. The load transfer from temporary to permanent structures is very important and requires some thought and a sequence. The overall stability of the structure, taking into account any openings that have been created. Are we creating a structure that looks like a block of Swiss cheese? If so, we need to have a lot of confidence in the load paths, as there will be very little redundancy in the supports for that structure. Is there a stage during construction that is not covered by the permanent works end condition? And by this end condition, I mean that if you have a structure that is being conventionally constructed from bottom up with stability mechanisms such as shear walls and bracing being constructed with the structure, then this worst case stability case for the structure is going to be when the whole thing is completed, i.e. you've got maximum destabilizing lateral loads from wind when the building is tallest. So therefore, by default, all previous stages are going to be acceptable. However, if the structure is being constructed in a slightly different manner, then this needs to be considered by a competent person to ensure that the structure remains stable during construction. And then finally, ask yourself, is this buildable? And has the load path been considered for the whole sequence, i.e. step by step? What we encourage is to visualize the process in your head, and you may spot a potential footfall, which can be eliminated in the planning stage and before we get onto site. So once we know about load paths and understand how the structure works, how can we use this to our advantage? Well, I've got an example here. So this is a project that covered the demolition of a 100-meter road in Saltley near Birmingham. The bridge was removed by John F. Hunt over 4 weeks in August and September to make way for the northern section of HS2's phase 1 route between London and the West Midlands. As we watch this, think about how the loadings onto the bridge deck is changing as its dead weight is removed. And then what happens to the load paths once certain structural elements are demolished. Load paths can be horizontal, such as when you see that they remove the steel beams in the middle of the deck. Think about how this changed the loading going to the abutments from any lateral support. So this is this center span being lifted out now. And then the end spans being cut and lifted away. The end span that was furthest away from the railway was mechanically demolished. So a crane was used there that you can see that was to remove the steel beams, and then on the far side there, that bay was mechanically demolished. So for this particular project, we were lucky because we had archive drawings of the bridge construction, which told us how the bridge was built. Therefore, we developed a demolition methodology that was the reversal of the construction sequence. And this is shown here in this annotation on an archive drawing with some of my annotations on it. So following this demolition sequence of removing the centre and then working out to the abutments, that assured that the structure would remain stable during the demolition works, as the load paths that during this process would be the same as those experienced during the erection sequence, because we've essentially just reversed it. And also that had the added bonus of the needs of temporary works was minimised as well. So this approach confirms that the bridge will remain stable throughout the demolition works, including when the free end is separated from the fixed end when the blue structure in the centre had been removed. There can be significant risks associated with latent defects in structures, a latent defect being a fault in a structure that could not have reasonably been discovered through inspection. So therefore, by following a reverse sequence of the construction sequence, we can be confident that the stability is ensured. And that's because we aren't relying on new load paths that may well be okay in theory, but the structure has not experienced them before, so they have not been tested, and therefore would carry a slightly higher risk. So here you can see some drawings that we provided for the scheme that outline the demolition sequence. Because we had knowledge of how the original designer envisaged the bridge had been constructed, how it was built, we knew that the stress changes in the structure and the support condition changes had less risk. We also proved this sequence through calculation ourselves separately, but it's always a good idea to try and maintain established load paths in a structure. And so the final point I want to cover before we get to our case studies with Angus is load history phenomena, something called load history phenomena. This is certainly something that can catch you out if you're caught unawares. I will explain it through a real life example that we had on a rail project where we couldn't drill and post fix a new beam into an existing column as the design life of the structure was 120 years and the permanent works designer could not get the guarantee for resin fixings for that length of time. So instead of drill and post fix, we had to break out and physically fix the rebar inside that column. So on the left hand side, we have the end product of what we wanted. That's a new beam shown in green attached to the existing column, which is shown in grey. On the right, we can see what we started off with, an existing column. The load path down this column is quite simple, and this load is spread evenly over the cross section of that column. To enable a connection, we had to partially demolish the column section to expose the rebar, and this meant that we only had part of the column left, and that was taking the existing axial loading through the column. The next step was to insert the new rebar, which is shown in red there, and inserting that into the void that we've just made. Now all the rebar was installed and fixed, we could recast the column and the new beam. However, where is the residual dead load stress acting? And also, where do any additional stresses get applied? The residual dead load or loading from the structure above at the time before recasting is applied to the grey section of the area of the column. This area is smaller than previous, and therefore the stresses in the column are higher in that localized area. Any additional loading into the column from above or from the new structure that is applied after casting is applied evenly over the grey and the green section of the column. But the grey part is already taking higher stresses, therefore this activity could push the column past its capacity. To sum up, once a structure is taking load, you cannot remove this load without some form of jacking or preloading. And casting wet concrete into this section does not remove any loading that's already there, although the new structure will take any additional loading that's added on top after it's cast. This is a valuable lesson that applies to construction and jacking, propping, especially back propping during reinforced concrete floor construction. So that's everything I've got to say so far on the subject in today's webinar. So I'm going to hand you back to Christian, and then Angus is going to take us through some case studies on the subject too. So I'll just stop sharing.
Thanks, Josh, yeah, so whilst we kind of get set up for the next one, I thought I'd take this opportunity just to remind you about our YouTube channel. I was just having a look. We've got more than 49 videos on temporary works and demolition, from whole webinars like this one to smaller case studies just picked out. I've put a link in the chat to get to those. So as I said, if you've got nothing going on this weekend, you know, there's something to keep you nice and busy. Yeah, it's well worth checking out. You know, mainly because, you know, I just want to make Andon YouTube stars. So you know, I'm going to keep pushing that out there. But that's also where we've had a couple of questions asking us about will we get the slides or the recordings from this? And we absolutely will. And we do put them up on YouTube, as I said, on Monday or Tuesday next week. So keep an eye out for that. And are we ready to go, guys?
I think so, as long as you can see my screen and you can hear me.
Yep.
Yep.
Yep. And yeah.
All right. Okay. So today we're going to go through quite a few case studies, but we're not going in depth on the full project here. We're looking at aspects of what Josh has discussed, which is load history, load paths, those items really. I think a point to mention is you don't always have to maintain the load path of a structure, as Josh was touching on. You can change the load path, but you've got to be damn sure as to what you're doing. I think that's the key point to take away. And if you can keep your load path, then keep it. Right, let's get going. So the first one, can you see my screen all right? Or was it blacked out at the top?
I can see it okay.
Looks good to me.
Fine, I've got a black bar up here and that's all. So the first one is Crawley. We've done a full case study on this previously, but this one again is talking about load path and understanding the structures to start with. That is the bridge we were demolishing. This was Econ Demolition. We're doing this for BAM, Nuttall, BAM, don't know what they're called now. Fairly simple, innocuous structure, you'd think. Though we had a bit of a fight on our hands to get our methodology accepted. So a little blue beam sketch I put together this morning. Main span over the tracks. The red are the columns. So the columns you can see there, and the other one that's hidden from view there. Stairs down, landing, stairs down. Same on this side with supports under the middle landing. And if you're looking at section, the black section, it would look something like that. Stairs coming down, the bridge deck itself, and the piers. So from site inspection, it's clear to us that this span here spanned from support to support with cantilever sections that picked up the stairs here and here. So the staircase was supported there and there and there and there. Now someone had put together a scheme where they were effectively insisting that we had to put some beams on here and here to pick up the cantilever section of the bridge. By a lot of messing around and discussion with our client and indeed their client, we persuaded them that that was not the case and we could do away with quite a lot of temporary works that really wasn't required during the small possession that we had available to get the bridge out. So our methodology was fairly simple: lift out the stairs and then you can lift out the main span. And because we didn't have any temporary works up on here, it could all start that much quicker and give us certainty that it was going to work. A point that's worth mentioning is when you're lifting, you often end up with, especially if you sling around a structure, you will end up with a horizontal component that the bridge probably hasn't seen before in its life. Simple solution to that is a push-pull or just an acro prop across, as long as it can take the theoretical horizontal load. Otherwise, you've got to try and somehow justify that parapet will work, even though it probably will. It's simpler sometimes to put a simple acro prop in place. Regent Street, again, it's been covered in a full detail case study. This is in Leeds, so it's not Regent Street in London, if you're wondering why you've never seen that. It's Regent Street, Leeds. Central span was post-tensioned either side spans were pre-tensioned. And the thing we're looking at here is to do with load history of the post-tension span in the middle here. So, gone too far. The proposal was to take out the central span with SPMTs, 4 phases, or it was 2 phases of the work, B1 and B2, and then B3 and B4 the following year. But the proposal was to take it out with a SPMT, and hopefully you can appreciate that the bending moment changes significantly from the current condition where it's supported here and here to the condition we're now talking about where it's supported here and here, where you get a significant hogging moment forming over the top of over here and over here. And with a post-tension structure, that is not ideal. So, oh, there you go, put it out so you've gone from a big sagging moment to one where you have a small sagging moment and quite large, well, fairly large hogging moments. This is the moment per beam. So load history again comes into play here, because you have to understand how the structure was built to understand the stresses in the structure in the current condition. The key issue being, is this slab, so the slab that spans from beam to beam, was that in place when the tension in the post-tension was installed, or was it not? Because that then changes the difference in the amount of tension, or sorry, the compression within the structure, and therefore the amount of hogging moment that it can deal with before failing, which in turn determines how far apart the SPMT supports can be. So again, it's a concept you don't hear very often, or don't hear being discussed very often, but it makes a big difference as to how a structure works and how it's going to behave. So by going through the historical drawings and everything we could find, our understanding of the construction was that the post-tension beams were constructed, stressed, and then they were lifted into position. The supporting information for this was the lifting eyes and the fact it didn't really work if you just picked it up without the post-tensioning. The deck was then cast in place, which means that the beams had to support the dead load of the wet concrete. That therefore means that the deck up here isn't in compression under the dead load on the structure. So that means that when there's no live load applied to the structure, there's pretty much zero stress, longitudinal compressive stress in that slab. Now that's important because when we start putting it to hogging, everything above the centroid here will start going into tension. You've obviously got compression over this due to the post-tensioning over this here, but this section here, I'm just going to draw in a different colour. What am I doing? I thought there was a rectangle tool. This section here was effectively with zero stress until you start bending it the other way, at which point the reinforcement steel starts picking up the tensile load. And it also means that all the post-tensioning forces are resolved within the beam itself, not within the combined CG. Whereas if it had been cast in situ with the deck and the beam, and then they post-tensioned it, those forces would have been resolved throughout the whole cross-section. So again, understanding the load history and how it was built made a difference to the analysis and where we could support it and the allowable hogging moments. So it's quite an interesting one to get your head around and try and figure out the current stress and then the stress that the structure was going to be experiencing when we started lifting it or moving it with the SPMT. So the next one, this was what you'd call a fairly run-of-the-mill job, or on the surface it was. We get a phone call from a client. We've got this new job, New Southgate. The permanent works engineer's given us a piling platform design. Can you optimise it at all? Fairly common. Get the scheme drawings. You think, okay, fine, that's fair enough. We can do something with that. We can look at our in-house methods for piling platform design and trying to thin it down a bit. And then you start looking on Google Maps just to get an idea of the site and where it is. And lo and behold, what's this here? It's a railway. What's this here? A big retaining wall. None of which was on any of the documentation that was provided to us. Then start doing a bit more digging, and you get this cross section sent back through to you. So you think, oh, development's up here, and then you start seeing things like assumed ground level, general overall ground level, and then you start thinking to yourself, hang on a minute, we put a retaining wall on here. It's just sketched in roughly typical dimensions. Quite a significant part of this site is surcharging that wall, and now we're going to run a 50-60 ton piling rig on the site. And then you find someone's already designed all of the working platform, and they've just excluded, or the client has refused to instruct them to do any sort of assessment at all of this retaining wall, and it's just been pushed out to the contractor saying, build this piling platform. A fairly frightening sequence of events. Network Rail hadn't even been engaged with to discuss this. There was no info on the wall and no time scale in which to go out there and start doing some SI. So not an ideal set of circumstances whatsoever, and just showed a complete lack of thought by the permanent works designers, who hadn't even flagged this as a hazard on their drawing, hadn't even crossed their mind that this should be flagged up as a hazard to anybody who was going to build this structure. And then when you overlay the plan, so this green line here is the toe of the wall, the blue line is the site boundary or the Network Rail boundary, and you can see how close we're getting with some of these piles. I suppose it's a relief that they'd went with a piled foundation and not with a raft, because that could have been awkward. So taking all that into account, we went back, solved the problem and came up with a solution. Required taking a lot of fill off, but given the lack of information, the lack of time to go and get any information on the wall, the best solution for the project was to keep moving, even if it required excavating a bit more ground. So we utilised the removed soil to justify the surcharge that we were applying behind the wall. The logic being, it's currently supporting that load at the moment. If we take that surcharge off, we can replace it with plant loads. And to make things even more interesting, we had piles at two different levels. So not only were the piles close to the railway, and there was no thought as to how it's going to be built, they then made this set of piles much lower than this set of piles here, which made the construction of the whole site even more challenging. Well, we got there anyway. We got around the problem. The next one, Spooner Row. I think I've done a mini presentation on this one previously, but again, talking about the load paths in this one. So that's the signal box, and we needed to save this bit here, which has now made its way to the North Norfolk Preserve Railway, where they're going to build a new brick base and restore it all to its former glory. So again, a simple structure, but by understanding how the structure currently works, you can come up with a simple method for actually lifting this bridge out in one piece. So from site visits, it was clear that the predominant loading is in this wall. I'm going to draw with a pen. This wall and this wall. I'll make that a bit thicker. Like that wall and that wall, they support, because the roof loads here and here, come down this wall here and here. The end wall, that end wall and that end wall are only really carrying the self weight of that timber panel, which is not really a great deal. So by understanding that, I'm sorry, I also meant to mention the floors also span left to right, so they're coming into these walls here and sit into this wall here and this wall here. So we needed to come up with a way to make sure we picked up the loads where we could. So the floor joists were very robust, shall we say, and the detailing of them was such that by supporting under those, we guaranteed we were picking up the rest of the structure. And they were quite robustly proportioned because of the loadings that were in there from the original signal levers, I think, because they were quite chunky even by the standards what you'd expect from the age when it was constructed. They were chunky. And then in addition to that, you had the strops that we detailed come up and around, and they pick up directly underneath the outer wall here, 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 and here. Same the other side. Again, because we weren't using a lifting beam because of headroom, we proposed that the horizontal component here and here was taken out by an acro prop across there. Again, simple piece of temporary work. It's very easy for the site team to install. In fact, all this was very easy, as you'll see in the video shortly. And by understanding how the structure works, you can understand how to safely lift it, and away you go. Just clear those drawings and I'll show you the video. This worked. See the white mark there is where they're going to knock the holes in for the beams to go across. Sorry, for the straps to go across, and on the ends you'll see shortly for the timber beams to go installed. Has everyone seen the video all right?
Yeah, I can see it all right.
Oh, all right. Someone was just complaining, that was all on the Q&A. And there you go. Out it came, nice and easy. All right, am I back to the presentation?
Yeah, all good.
Perfect, right. So the last one is gramophone works, which I think Richard did a presentation on. I don't know how long ago it was now. Probably last year, maybe the year before, in fact. Yeah, probably the year before. So gramophone works was an old gramophone works in London. Again, a very robust building, and the reason being it's where they used to cut and copy gramophone recordings. I think if you got vibration, it would affect the quality of the recording. So they built this big robust building to try and reduce vibration, from what I could see, because it had columns in it that were something like 4 foot diameter. So each of these circles, in fact, represents a column. So they were big chunky columns. Now, as is often the case, where they want to keep the majority of the building and put some more floors on it, there were lots of holes to be opened up in the structure, bits of slab to be taken out, etc., to allow the new vision for the structure. I think there was a new core was coming up through the middle here, new stairwell over here, and I can't remember what was going on down this end. Anyway, that's what the permanent works engineer wanted. That's what the permanent works engineer gets. So again, you have limited information about these structures. You might have a bit of SI from one bit of a slab or another bit of a slab. You might have a couple of cores where you've got concrete strengths. You might know steel grades if you're lucky, etc., etc. So again, if we can, we try and maintain the load path and also the bending and the shear forces that the structure experiences fairly close to those that it's already carried in the past, that we know it's carried. So the way we approach propping of a structure like this is by analysing the structure in the current condition, which is the top image, seeing what the bending moments are in the X and the Y direction, and then you run the same analysis again with the slab without the supports in place, and from that you can work out where the moments have exceeded the previous sort of design moments. So you take this as your allowable moments effectively on the structure, and then you compare that to what they'd be without any propping, and you work out where the moment's going to be exceeded, and you place some propping. And there you go. So from that we could work out where we needed to prop and where we didn't. There it is. Run through, put the propping in place, and then I think we even did I haven't included it. We then do another analysis with the propping in place just to demonstrate it. But the principle is to maintain the current load path and current design moments or current allowable moments, allowable shears, and maintain that throughout. Otherwise, you've got to know more about the structure and you're pushing it harder, which is not necessarily a good idea. And yeah, that was all done, dusted, and it minimised the amount of propping that we needed throughout the structure, at least until they started demolishing it and they found that a lot of the concrete was effectively like sandy dust, and the extent of the analysis, the extent of the structure that was demolished was increased quite rapidly, so there wasn't a great deal left. Well, there you go. Right, I think we're almost there now. So, do you want to jump back in, Josh, or do you want me to carry on with this bit?
Well, shit, yeah. Essentially, this is just a rounding up slide, really, of what we've looked at and the load paths. I hope everyone's learned a little bit today on the importance of understanding the structure and understanding the sequence of the construction or demolition, as it were, and the understanding the problem to get the right solution, really. But yeah, that's been load paths in a nutshell. If you want to know more, if you skip to the next slide, Angus, there's lots of information out there on the Temporary Works Forum, constructability guidance. There's a constructability, an early focus on constructability in temporary works, which is by Safe by Design, which is a work group by Network Rail. There's also Temporary Works Principles, Design and Instruction, shown on the bottom left there with the yellow bands. That's a really great book on temporary works, delving into lots of different areas. There's the Code of Practice for Full and Partial Demolition, 6187, which I discussed.